This is a continuation of the earlier video on this assembly example. I had to cut it at 15 minutes to fit on YouTube. I was going to jump down to the very bottom of the program. We're going to jump over this subroutine because one important thing is down here. The interrupt vectors in program start. C automatically says when you say main, it puts down automatically on what's called the microcontroller's reset vector location. It puts the address of the main function. Assembly doesn't do that for you. What are we doing? We're saying go to hex FFFE, that is the address of the startup vector. Then we're defining a constant, which is the address of the init start function. The very first thing that a microcontroller does when it powers up is it looks at this hex address and loads whatever is there into the program counter. That's how it knows where in program memory to start. If you look up here, you'll notice that our program memory actually starts with lookup tables. We can't run this string as a command. That would lead to craziness and sadness. Instead, we need to start right here to init start. Well, it's not unusual to put your constants up front. It's not unusual or prohibited. So then you have to provide a mechanism by which you tell it where to start in the code. Where does the executable start? What's the first line? And that's this reset vector. So any assembly program will have something like this. It's worth mentioning that Freescale provides some macros to do this, and it's possible that if you look at example projects that they don't include this statement exactly this way. They'll use a different macro. Mostly that macro is this xdef entry main thing, but the same concept is there. If you forget this, your microcontroller will do nothing. Okay, this brings us to the last part of this code. I wrote a quick subroutine. I only wrote one. It's not actually the one that was referred to by the main program. Printdesc is intended to print the USB descriptor. That descriptor was that lookup table. Now, often the word lookup table means somewhere where you'd want to go in and catch the ith element of it. We might check your ADC and look up what that corresponds to. In this particular case, we're going to just spit out the entire descriptor to the SCI, but I wanted to just show you how one might interface with something out in program memory. It looks very similar to what you would do somewhere else. So this is a subroutine. Subroutines are not interrupts. They do not store the various registers that one might wish to be preserved. If you run a function, calculate area, and it changes variables out in memory, you would be a little upset. So it's good form to put a bunch of pushes and pulls right at the beginning and end. And you'll notice that these are in opposite orders. If A is the last thing that's pushed, it needs to be the first thing that's pulled. If X is the second to last thing, it needs to be the second to last thing. These commands are inherent addressing mode. I'm not going to look them up and tell you what their opcodes are. It's not complicated at this point. They're just 1 byte opcodes. They don't need an argument. You just put it onto the next spot in the stack or take it off from the next spot in the stack and move it to the register. Similarly, clear H and clear X we've already covered, so I'm not going to spend too much time on that. I don't need to clear A, by the way, because I'm going to use a load command that's going to overwrite it. So the very first thing to talk about is that in order to go from the first element to the nth element, if there are n elements in this array, I want my I, if I'm going lookup I want I to range from 0 up to n minus 1. The way that I've chosen to do this is I've chosen to go ahead and grab the byte that we see, trusting that it's at least 1 element long, and store that to the SCI, so then we're done. And then this section here is going to increment the X value, check to see if we're past the end of the lookup table, and then go back to print another character if we're not past the end of the lookup table. After that, we're just going to do the polls, and then this is return from subroutine. So that's just changing the program counter. Again, this is a subroutine, not an interrupt, and so it does not automatically do the stacking, and we need to stack, unstack, and then return. If this was an interrupt, then we wouldn't have this command or this command or this command or this command. You'd probably still want to push and pull H, because for compatibility with the HCSO5 family, interrupts don't stack H. It's really suggested to go ahead and do that yourself. C pretty much automatically does that for you. In the case of an interrupt, this RTS would be an RTI, which is return from interrupt, and assembly has to have a different command for return from interrupt versus return from subroutine, because interrupts have that stacking. And you have to have a different command that tells the microcontroller, unstack the accumulator, X values, etc. I suppose if you got really, really clever, you could save a few lines of instruction code by using the return from interrupt, but if anyone ever saw you do that, they'd be a little upset with you in terms of readability. So let's return then to this center piece. This is the only piece that we don't understand. The first line is add immediate to X, and then it has an immediate value of 1. Now I don't use IncX because IncX only changes the X register. This add immediate does correctly handle the H as well. So if X was FF, then adding immediate to X of 1 will roll over H. So now the HX register will read 100, hex 00. If I used IncX, it would roll X back, but would not track that in H. IncX only affects the X register. So I'd have to, if I knew for a fact that the USB descriptor was always less than 256 bytes, then I could use IncX to be slightly faster and more compact. But if I think that maybe someday this descriptor will get super long, I should leave it as add immediate. Then this was the thing that I wanted to talk about. I'm going to compare it to an immediate value, but that immediate value is really weird. So I've said it's an immediate value, but then I've just got here these two things. Well, lookup end and lookup were defined up here. And I know that that's E23 and E000. The difference is that I, as a programmer, didn't have to write down those values. I didn't put something here that's the length of a string. This difference is going to be accurate even if I come back up here and change this string and take out a word or something. I don't know how long that is now, but the difference between these two labels will be the length of the string. And because we do that, we swap this out. We say E023 and E000. We can go ahead and do math on them. That gives us hex 23, and then that's a good immediate value that I could put in. So this, just for completeness, would be CPHX. This compares the index register, the 16-bit index register with memory. It would be 65, and then that value that we wanted to check. But this is a 16-bit comparison. And this is cool because this allows us to have really, really long descriptors, which if you've ever looked at a USB descriptor, they're super long. So I wanted to show this as an example of one way that you could have really long loops. Now you could also do this if you wanted to with the move instruction. It has that special IX plus mode, which you could just do that. If you wanted to zero terminate your descriptor, you could do that as well. But this here is a branch if lower or same. So again, all comparisons, all of the branch statements are intended that you'd load the register. I'm going to say with A, we would compare or subtract if you prefer B, and then the branch statements are all written with the idea of A blank B. So in this case, because I say branch lower or the same, that saying is A less than or equal to B, then branch. So that'll take me from here up to there until the time that I am equal to N. Okay, that's actually a problem. Okay, so we found another bug because this says branch lower than or the same, and in fact we want to just branch if it's lower. Once it becomes the same, we want to end because we're taking I from 0 to n minus 1. That means that once it becomes n, we want to go ahead and call ourselves done. So I used the wrong branch instruction there. So we don't want this less than equal to, we want that to just be less than. Now one last note is, why did I use BLO and BLS instead of branch less than or branch less than equal? If you look in your book, you'll see that you do have those different branches. And the answer is this: you always load the register with the first value that you're interested in. Then you always compare or subtract the other value that you're interested in. The difference between a signed and unsigned branch is how you interpret the relationship between them. So if you look at BLO, that's branch lower than, it's an unsigned comparison. If you look at BLT, that's branch less than, and that is a signed comparison. So the same number for A and B, if A and B are signed, for example, if A was 0 and B was FFFF, which is -1 in signed arithmetic, branch lower would branch because A is lower than B, A is less than B in a unsigned sense, whereas in a signed sense, A would be greater than B, so you would not branch. The way that's handled is by using different parts of the condition code register, which is a level of detail you're not expected to know, but you should know. There are signed and unsigned branch instructions. You use them identically. The only difference is how you wish the numbers to be interpreted. Are A and B signed? Then you use a signed branch instruction. Are A and B unsigned? Use an unsigned branch instruction.